Hi, everyone. I'm really excited to be here. First time at Canada, and first time at SecTor, of course. So really, thank you for joining me in my session from Days to Hours, Accelerating Cyber Threat Response with AI Agents. My name is Yuval, and probably the most important thing to know about me is that I'm a chess nerd. So I'll grab a chess game every 5 minutes spare I have. Other than that, I have give or take 13 years of experience in both offensive and defensive security research. I've been to the IDF, the Threat Intelligence Force 8200, for more than 7 years, mostly offensive security roles. And afterwards, I joined Hunters as the Director of Security Research and AI. For those of you who are not familiar with Hunters, it's basically an AI native next-gen SIEM platform. Builds an autonomous agentic platform to triage alerts and comes to verdict, whether they're malicious or benign. So a lot of, from what we're going to talk about today is lesson learned from what I did there, but basically this has nothing to do with what Hunters does, and also not with my new project. This is a total sidekick, something I did on weekends, so a total hobby. I hope you enjoy the session, and let's kick it off. So today we're going to talk about an agentic system to identify, triage, prioritize, and create visibility and hunting queries for emergent threats. But a second beforehand, we will talk about why do we even need such a system, and what is it built for. Afterwards, we're going to deep dive into each and every component within the structure and understand why is it built the way it is. What were the design choices that I made, and why does it work like that? Afterward, we're going to see a quick demo, a demonstration of the system works and what its output. And then we're going to talk a little bit about evaluation. So for those of you who have some experience with building LLM applications, bringing it from crude prototype to actually production-grade system is quite a heavy lifting and might be the most challenging part. So I'm going to talk about how to evaluate such systems and make them actually useful. And last but not least, we're going to talk about the future. What can be done here? How can we continue and expand this project in the future as well? Amazing. So in a quick show of hands, how many of you recognize these emerging threats on the screen on the left? Cool, so quite a lot. And that's not a coincidence, right? These are all emergent threats that we had to pay attention to give or take the recent months or the recent year. And it takes actually a lot of time to actually understand and identify that something like that is happening. And just a moment before we will dive into how can we shorten the time window to actually respond to these kind of threats, let's define an emergent threat, right, and what we're going to deal with in this session. So when talking about emergent threats, I'm not only talking about traditional vulnerabilities, which are usually tied to a specific software flaw that can be patched. So here I'm going to use a broader definition for an emergent threat that will also include compromised credentials, supply chain weaknesses, and even misconfigurations that start generating buzz on social media and therefore are now more exploitable. Okay, and this kind of stuff requires us not only to implement a specific technical fix, but also some maybe detection policies or detection mechanisms or new policies, or rotate all the keys, like the Snowflake breach from last year. So a lot of different different things that we need to do in order to actually respond to these kind of threats. And to be honest, everything here takes a lot of time. Identifying that something is happening, understand whether we're impacted or not, and understand what we need to do and actually apply the mitigation. How much time is it taking? So that's a great question. When talking about the threat lifecycle, we can divide it to 4 different stages. The first stage will be the initial discovery. And this is the very first moment when an attacker or a researcher identify that the issue exists. So it's fine, the security issue now exists, but it's not yet widely known. The second stage will be the public disclosure or the public recognition. This is the very moment that for traditional vulnerabilities, for example, the vulnerability is now listed on NVD or NIST or some public list like that, CVE database. For a broader definition of emergent threats, this could be when the issue is reported in the news, for example. And the time period, the time duration between the first discovery to the public disclosure is actually unknown. And that's not a big surprise, right? It's very hard to tell when the issue is first discovered. But this question mark is something that, as security practitioners, we just cannot accept. The third stage is the official patch release, or the mitigation guidance. So this is when, for traditional vulnerabilities, there's actually patch, the vendor release, security mitigation, some technical fix that can be applied to the system. For our broader definition, that would be when a security research firm publish an advisory, right, and guide us what to do. And the time duration between the public disclosure to the official patch release can take between a week or 2 weeks. So this is the time duration between the very first moment that we know that something is happening. There is something that's happening out there, but we just don't know what to do with that, right? And we're going to call this time period the gray risk phase. The last stage, of course, is the full mitigation. That's when we're applying the fix, we're mitigating the threat, we implement the detection mechanism. Now the policies are all in place, and from the moment that there is an official patch release to the full mitigation, it can take 80 to 100 days, which is a long, long time. And for those of you who've ever been to application security team, that's a compliment, right? Because that can take much, much longer, and the SLA for less than critical vulnerabilities can take even much longer time than that. So in this session, we're going to mainly focus on the black risk phase and the gray risk phase. And that's because in this critical period, it's either we just don't know, something is happening, but we're not aware, or something is happening, we are aware, but we just don't know what to do. And that's the very time that we're going to talk about in this session. So now imagine, the additional timeline, and that's a timeline when an attacker is actually aware of the vulnerability. He knows he knows that there is something going on to the very first moment that it can actually exploit it. And here, I'm sorry to tell you, I don't have good news. This research was published last year by IBM researchers, where GPT-4 was able to correctly exploit one-day vulnerabilities 87% of the time. And that was 13 different vulnerabilities that was tested. 12 of them were exploited successfully. Since then, there were so many research papers that got released, including LLM agents that can autonomously hack websites, including new benchmarks. So we can now empirically do empirical evaluations and get better and better with the way that we're exploiting vulnerabilities. That's not good for us as defenders. This graph is taken from one of the autonomous pen testing companies that actually try to automate the pen test process. And we can see that the models are doing better and better in offensive security tasks. So just to recap everything we just discussed, we have a lot of different kinds of emergent threats. It's all required a lot of times from us, a lot of attention. We need to identify something is happening, understand how to tackle, and what do we, if we're even compromised or can be compromised if we're exposed, and to apply the mitigation. Everything takes a lot of time. And the time window, the defender window, the time window that we have in order to react and respond to these emergent threats is only getting shorter and shorter when exploitations are actually becoming kind of commodity. And that's what led me to build this system. So what we see here is basically a multi-agent system to identify, analyze, and create threat hunting queries according to a specific business context of a specific organization for emerging threats. And I know it can be a little bit overwhelming, but don't worry, we're going to deep dive into each and every component here. So let's start right away. So the first thing we're going to do is basically to ingest social media data. And just for intuition for why are we even doing that? So as we mentioned earlier, the critical period that we're going to deal with at this session is the black risk phase and the gray risk phase. So that's the time before the public disclosure and after the public disclosure. And in this graph here, we see this is taken from a research that was done in the University of Florida a couple of years ago. And we can see that even in the gray risk phase and the black risk phase, there are still posts being published on social media. This research was done on Reddit, on Twitter specifically. But as a practitioners, we know that there are posts on other communication channels as well. Sorry. So the first thing we're going to do is to ingest social media data. How do we do that? So we're basically going to look for specific subreddits, specific X influencer, and do some kind of generic keyword search over both Twitter and Reddit. And we're going to bring in everything: the title, the body, the author, the engagement metrics, everything we can. The next thing we're going to do is that for each batch that we're going to ingest, we're going to send it to an LLM and ask for it to cluster the social media posts according to the specific security issue, if exists, right? If not exists, we can dump it. But the thing here, and maybe the great opportunity that we have now with the rise of LLMs is that traditionally we used to use traditional machine learning algorithms for such clustering mechanisms, such as HDB scan, right? But here we don't always have a keyword that we can cluster accordingly. If we're in the black risk phase, there's no CVE assigned. And we also have a broader definition for an emergent threats, right? So it's not always a CVE. So we do semantic clustering using LLM. And we send each batch to an LLM and get some list of clusters regarding to the batch specifically. Afterwards, we will do some post-processing mechanism that we will send the clusters from each batch, and we basically merge them. So now we're going to have, as an output, a long list of clusters, includes for each cluster the topic, the reasoning, why these posts were clustered together, the list of the posts themselves, of course, and the size of the cluster, and the engagement metrics, which is basically summarization of the engagement metrics for each post on its own, including upvotes, retweets, reposts, everything that you can imagine. So that's the output of this stage. The next thing we're going to do is basically to ingest threat intelligence authoritative sources. So everything you can imagine, including NIST, CISA alerts, Patch Tuesday, AbuseCH, basically everything you can imagine, and of course, much, much more than that. And the reason is that also, we want to provide a grounded foundation for our model to actually learn from and to have verifiable data that it can use down the pipeline. But also, it's very important for us to distinguish whether we're in the gray and black risk phase or in the white risk phase. And now there's a CVE assigned that we know where we're at, right, in this timeline. So what we do here is basically we ingest this data, we parse it, and we're going to feed it as a context to the model later on. Cool. So now we have all this all the social media clusters ingested. We have all the data from authoritative threat intelligence sources. And now it's time to kick off our agentic system. So the first agent we're going to kick off is the threat identifier agent. So this agent gets as an input the business context of the specific organization. So that includes the sector, whether I'm financial institution or healthcare company, right? There are different threats that I need to be worried about. The tech stack. If I'm using Azure or GCP or AWS, if I'm using SAP, I'm using Okta as my identity provider. So what is actually the SaaS application that I'm worried about? What's my tech stack? If I'm using RDS, databases, etc. And of course, what specifically threat types should I focus on? So for example, I care more about social engineering than Android vulnerabilities, okay? So that's also important to feed the model with the specific business context. Then the threat identifier agent has access to two different tools. That's Perplexity and Access Search. And it uses curated prompts to actually search across the internet in a specific time frame that was defined previously by the user. And it will search for vulnerabilities or emergent threats in general within this specific timeline according to the specific business context that was provided by the user. And the output for this agent will be a relatively long list, can be a dozen of different emergent threats with the title, a short description, and a couple of reference from where it was found. So now we have all the social media data ingested, all the data from the threat intelligence sources, and we identified a bunch of emergent threats by our AI identifier agents according to the specific business context. And the next thing that we're going to do is actually to prioritize all these threats. So the threat analyst agent gets as an input everything that we just talked about, all the structured sources and the emergent threats that were identified by the AI identifier agent. And actually dedupe them, of course, right? It merges threats from different resources, but also retrieve more context and enrich the emergent threats with more context, so it will be able to prioritize according to parameters that also defined by the user. And of course, we have some default in place. So it also includes the exploitation status, affected systems, relevance to the target sector, and everything that you can imagine that we can prioritize emergent threats according to. And basically, the threat analyst agent has also access to Access Search and Perplexity, but this time, it won't use it to search widely across the internet, but to retrieve, to semantically search for similar blog posts or similar advisories that were published according to these specific threats, and to enrich them with more data and understand whether it's relevant to me or not. So the output from this agent will be a short list between 0 to 2, limit 2, emergent threats that we now want to respond to. Amazing. So we currently have all the structured sources ingested, including threat intelligence and social media data. We have all the AI-identified threats. We prioritize them, so we have between 0 to 2 different threats now we want to react to or we want to triage. And now it's time to power our threat hunter agent. So the threat hunter agent gets as an input, of course, the threats, the most prioritized threats with all the enriched context and all the references provided to him by the threat analyst agents. And its job is basically to extract indication of exposure, indication of compromise, techniques, whether it's if it's a threat campaign or a specific attacker that we're trying to identify here, and to generate from all of the above Snowflake OCSF-based SQL queries. So let's dive into it. Basically, the threat hunter agent is a node in the graph, okay, that includes a subgraph. And this subgraph is split into 2 different agents. So the first one is the signal extractor. The signal extractor is basically receiving all the references from the threat analyst agent and try to extract indication of exposure and indication of compromise as discussed. It doesn't always have all the data it needs. And why is that? The threat analyst has one job, and it's to prioritize the alerts. The signal extractor looking for something else. It looks for the vulnerable versions. It looks for indication of exposure, of compromise. So it needs different data. So sometimes it doesn't have all the data it needs when we're at this stage of the graph. And at this point in time, the signal extractor can delegate tasks to the threat analyst agents to retrieve more context according to the references that it already has in the current context. So imagine that if sometimes we have a post on Twitter that has a link in it to a GitHub or to a list of indication of exposure. So the signal extractor agent can delegate this task to the threat analyst agent to fetch the entire list of indication of exposure. And that happens a lot. And the next node in the graph will be the query generator. The query generator goal is basically to turn a SQL, to generate a prompt according to the signals that were found and turn it to a SQL query. And it uses another tool for that, which is the prompt to SQL tool. So let's dive into how this tool is actually working. So just a minute before, we just mentioned that the SQL queries will be OCSF-based. For those of you who are not familiar with OCSF, it's the open source cybersecurity schema framework, which contains a lot of different schemas. This is just a subset of them. So also, file system activity, authentication logs, network activity. So basically everything you can imagine. It's basically a data model for security events. So a lot of big vendors are using this data model, including AWS and CrowdStrike. So it's very easy to extract your data from these vendors in this specific data model. So this is the reason I used it. But also it's very detailed. It has very detailed documentation out there. So it was very complementary to me to use it to feed the model with the right context. And we can see it right here. If you look specifically on the process activity class, or the process activity schema in OCSF, we can see that there is the table with the column names and description of each one and the type of each column. So I used it to my benefit. Oh, oops. You didn't see that. Cool. So for each, so how do we do that? How do we convert a natural language text into an OCSF SQL query? What we do is to transform each OCSF schema to a semantic model, which is basically a YAML file that contains the name of the table, the columns in the table, and of course, the descriptions that are taken from the OCSF public documentation, the relationships between different tables, and between the different objects, also taken from the OCSF public documentation, and a lot of sample queries. So curated queries that we know that are working and make sense. So a lot of examples for that. And last but not least, synonymous. Synonymous actually means how do one refer to this table if he'll try to put it in natural language text. So for example, for OCSF 3002 authentication, a person will refer as authorization, auth, logins, logons, a lot of different things. So we can actually use that to understand what is the most relevant schema according to the prompt provided by the user. So how is the magic happen? Basically, the SQL generator agent will generate a prompt. For example, search for a network connections for the specific IP address, assuming it's an indication of compromise. The next thing that is going to happen is that we want to understand from all of OCSF schema models, from all the different schemas, which schema is the most relevant, or which schemas, because we might perform a join as well, which schemas are the most relevant in this specific context. And we don't want to provide the entire schema model for all those schemas, because there are so many of them, and of course it can get quite big, and we don't want to blow up the context window of the model. So we're using a RAG mechanism here to retrieve the top K. In our case, it's the top 3 most relevant schemas for our specific prompt. So once we retrieved the most relevant schema model, we can send it to LLM and generate the SQL query that is correlative with this specific prompt. Once we will generate it, we will test it using internal Snowflake function to make sure that the syntax is correct. And if it's not correct, we have some kind of feedback loop to generate the query and then try it again, generate the query, try it again, top 5 times. Hopefully, it will be shorter than that. Cool. So we have all the data ingested, including social media data and authoritative threat intelligence sources. We now identified additional emergent threats by our AI identifier agent. We prioritize the most relevant ones according to our business context that we got as an input. And we created visibility queries and hunting queries to understand whether we're exposed or compromised. Now it's the time to actually generate the final output, summarization of the thread that we can share with our stakeholders. And for us, it's the time to see a quick demo. Amazing. So what we see here is basically, do you see the full screen? Better, right? So what we see here is a US-based financial institution. The tech stack includes Microsoft 365, AWS, SAP. Remember this one, it's important. And the critical system includes payment processing platform and customer data repositories. They are particularly concerned about ransom and data theft. And on the left side of the screen, we can see the agentic workflow in process. So of course, it's 5 times faster than in real life. But we can see that the agent is actually extracting indication of exposure and indication of compromise and generating SQL queries accordingly. Now we can see the list of identified threats. We have here in this day, we have 5 different ones. Prioritize threats. So of course, we prioritize the sub-vulnerability on the day. So it was and we have also the references that are provided by the threat analyst agent. Here we see the hunting queries that created, so the signals and the hunting queries themselves. And the, of course, summarization. That's it. Cool. So let's talk a little bit about evaluations. So why do we need to evaluate LLM applications? Very a funny question, but actually, why do we need to evaluate it? So basically, LLMs are not deterministic. I'm not telling you something that you probably don't know, right? So it's very hard to tell if it's consistently useful. So to actually make sure this system is useful, we need to build a very comprehensive eval suite. So that's the first thing. And then the second factor here is that if we want to change a model, if we want to change something, to tweak the prompt, to change something, we need to make sure that we don't break anything. So we can think about it just like as you think of unit tests, right? We want to make sure that we don't break anything, so we need to actually have a way to evaluate ourselves. But how do we do that? So exactly like unit tests, we need to compare the expected output to the system output. But it's not always easy to do that with exact match. When possible, we will always prefer to do that using exact match comparison. If we can't, we will do that using semantic match comparison. And if not, we will use LLM as a judge. So we will give examples for each and every evaluation mode right away. And of course, human in the loop, always important. We have to eyeball the results, understand if they're useful or not. It's always helpful. Amazing. So is that a slideshow? Or you can see my... better now. Amazing. So what do we even measure? What do we measure here? So for the threat identifier agent, we want to make sure that we're identifying the relevant threats. That's pretty intuitive intuitive. For the threat analyst agent, we want to make sure that we prioritized the right threats and that we retrieve the right context. And keep that in mind, because if we prioritize the right threats, maybe it's not necessary to make sure that we retrieve the right context. But that is, and we will talk about it later on. For the threat hunter agent, we want to make sure that they find the correct signals and that we create accurate hunting queries. And for our final output, we want to make sure that it's actually grounded, accurate. We didn't made up anything, right? That doesn't hallucinate, and of course that it's actionable. So okay, so what is the ground truth and how does it look like? So basically our ground truth is the data set that we're going to compare the system output to the actual golden data set, to the actual ground truth each time. And for each different test, it's going to be a comparison by other evaluation mode. So how is our ground truth actually built? So for each date and for each business context, and in the ground truth scenario, I ran the system once a day, but of course it's going to be determined by the user when running the system itself. So for each date and for each business context, I'm going to have a list of expected identified threats, a list of expected prioritized threats, and then for each threat in the ground truth, I'm going to have the context pages, the indicators, whether they are indicator of exposure or indicator of compromise, and the database hits. So instead of comparing the SQL query to an expected output, I'm going to compare the actual results that was retrieved by the query. And we will talk about it in a moment. And a reference brief that, of course, we want to compare to the system output. So how do we measure each and every test here? So the first thing that we want to evaluate is whether we identified the right threats and prioritized the right threats. And the way we do that is with semantic match comparison. And why is that? If you remember, in the beginning of this talk, we talked about clustering using LLM. And that was because we don't have a keyword. We don't always have CV assigned to this emergent threat because, A, it's not yet publicly disclosed. We're in the black risk phase. Or B, it's just not a vulnerability. We have a broader definition of an emergent threat. So we can't do exact match comparison. If we can, we do. We can use a regex to extract it, and we do exact match. But most of the time, we won't be able to do that. So that's for the evaluation mode. And what do we actually measure here? So in each case, we would like to measure recall and precision. For this specific case, in the identified threats, for example, we only care about recall. Okay, I don't care if I identified 20 more threats. I only care if I identified the right threats that going forward will also be prioritized. So recall basically means from all the threats that the system should have been identified, how many of them the system actually catch. Okay, that's recall. And for prioritized threats, I only care about precision. I only care from all the threats that the system identified, how many of them are actually correct. So that's precision, and that's what I care about, the prioritized threats. So that's what I'm going to measure. Next thing is context retrieval. And I want to make sure that the context pages compared to the that are in the ground truth compared to the output of the system itself are equal, basically, okay? So, and that I can do, of course, with exact match. Also, I only care about recall, and the reason here is that the internet is changing. There might be a new blog post tomorrow on the same specific security issue, but I want to make sure that I am identifying the right context and retrieving the right context so I later on can build the rest of the pipeline and identify the right signals and create the queries, etc. And the reason that I'm actually performing this test is because we don't, we want to divide the metrics here, the evaluations here, to the smallest unit as we can do, right? Because if something will break, if we won't prioritize the right threats, we want to be able to say, okay, that happened because I didn't retrieve this and that. And to make sure that we actually break it to the smallest components so we can be able to identify what were the flaws with the model change, the prompt change, etc. And exact match comparison is very helpful here. The next metric that we're going to basically evaluate is that we're identifying the correct signals. Here we can also use exact match, and we also use recall and precision. For query accuracy, as mentioned, we could have been just compare semantically the SQL statement was the output of the model to the actual SQL statement in the ground truth. But instead of doing that, we're executing the SQL query that was generated by the system on our test database to make sure that we retrieve the right rows. Okay, and we do that because we want to transfer the evaluation mode from being semantic comparison of SQL statement to an exact match, to make the tests as deterministic as possible. Because in the world of non-determinism, that's very important. And that's a very good lesson that I learned during this process. And of course, for the final summaries, we have LLM as a judge that will compare the summary that is the output of the agentic system to the summary in the ground truth. Cool. So what's coming next? So basically, the system currently ingests data from Twitter and Reddit. In the future, I would like to expand that and also ingest data from Telegram, Discord, other open sources as well, because we know that attackers live there as well. And of course, create some dark web accounts to infiltrate data from the dark web as well. That would be highly beneficial for this kind of system. Next, I want to have a deeper SIEM integration. And why is that? Like currently, we get as an input from the user the data sources, the technology stack, the tech stack. If I would have a SIEM integration, I would be able to identify what is your tech stack. If you're ingesting Azure audit logs, I know you're using Azure. So that would be very much like the high accuracy and much more coverage to your tech stack if I'll do an integration with your SIEM data. And of course, I can also discover what are the critical assets and map them, etc. And currently, we only support SQL Snowflake-based queries, OCSF-based. In the future, I would like to also support additional SIEM query language like SPL, KQL, whatever it is. Another thing is that currently we're not executing the query itself. We only generate it. So in the future, I would also like, with a deeper SIEM integration, to execute the query and retrieve the results and have some kind of feedback loop so that I would be able to tune the query and actually understand if it's useful or not. If I have hundreds or thousands of results, might be okay, might be too noisy, so for a person to handle. Cool. So to recap everything, we talked about a lot of different things, right? There's a bunch of emerging threats out there. Every other day, there's something else that requires our attention, whether it's to identify it, understand whether we're impacted or not, and apply the mitigation. Everything takes a lot of time. And with the rise of LLMs and generative AI in general, exploitations are now kind of becoming a commodity. The time window that us as defenders have to protect ourselves from these kind of threats is getting shorter and shorter. That's why we have to embrace AI, and we have to transform the way we act from reactive approach to proactive and AI augmented. And that's it. Thank you so much for joining me.